Good morning, everyone. A warm welcome to all participants to the second day of 6-day National Online Faculty Development Program on Advanced Communication Systems Shaping Next Generation Networks, organized by the Department of Electronics and Communication Engineering, Jyoti Engineering College, Thrissur. It is a great privilege to introduce our distinguished keynote speaker for today's first session, Dr. A. Unnikrishnan. Dr. A. Unnikrishnan is a distinguished scientist who served as Associate Director and Outstanding Scientist at the Naval Physical and Oceanographic Laboratory, Kochi, one of India's premier defense research laboratories specializing in underwater acoustic systems and communication technologies. An alumnus of Indian Institute of Science, Bangalore, he brings decades of expertise in electronic and communication systems within the defense and national security domain. His extensive experience at DRDO encompasses research in advanced communication systems, acoustic signal processing, and technology development for naval applications, making him a highly regarded voice in the evolution of communication technologies in India. Today, Dr. Unnikrishnan will be sharing his insight on a topic: what do you purpose to do? What all can you do? That is highly relevant to the evolving landscape of communication technologies. We are certain that his session will provide valuable knowledge and perspectives to all participants. Sir, we are honored to have you with us today. On behalf of Jyoti Engineering College, I extend our heartfelt welcome and gratitude for accepting our invitation. Without further delay, I respectfully invite Dr. A. Unnikrishnan sir to take over the session. Thank you, sir.
Good morning, everybody.
Without further delay, I respectfully
Good morning, sir.
Good morning, Dr. Sojanlal and all the participants. I would like to share my thoughts on communication engineers. As you march on, what do you propose to do, what all you can do? Just to give a perspective of how much we have achieved, what more can you achieve in the days to come? Let's look at how exactly the discipline of communication engineering originates. Thanks to the heavy demands on communication, that is terrestrial communication, wired and wireless, satellite communication, internet and IoT. Largely this happened because of Second World War. Because during the Second World War time, we thought war could be fought across the continents also. Otherwise, most of the wars were restricted only to the neighborhood only. Second World War taught us, gave us an insight that war can be taught across the continents also. There was a requirement to communicate, and that was one of the motivating factors. Other supporting factors could be developments in instrumentation, signal processing and modeling, analog and digital circuits, device technology, the physics and the fabrication and all that. All became the exclusive subjects for the electronic engineers to specialize and contribute towards the development of communication engineering. At this point, let's remember, thankfully, Maxwell's famous equations. I've just given mark 2 of them, which shows very clearly that the signal can be transmitted across the continents on wireless media. Essentially, it says how the electric field and the mechanical field variations can be used effectively to transmit the signal across the globe on wireless media. So what do the communication engineers do? They design and develop and operate communication systems, corresponding circuits, techniques, algorithms, equipments, transmission systems, and all that to transmit voice, data, images, video, and audio-video commands and everything. We have wired links, we have wireless links, we have terrestrial links, we have satellite links, all those things. And this is what the communication engineers try to develop and operate. Let's have a look at the communication receiver. If you look at the communication receiver, these are the components. There's a transmitter, then there's a medium, then there's a noise, then there's noise corrupting everything, and the receiver. And of course, the we transmit a signal PT, transmission, there's a transmission log of 20 log R, there's a noise corruption, and finally the communication engineer's job is to recover a signal. So the communication engineer, in effect, it takes care of the transmitter and the receiver. For that, if you look at that equation, famous equation of the signal reception is PT minus TL minus NL plus DI should be greater than the threshold for detection. As you know, remembering this equation is very straightforward. What are that are bad or negative, what are that are good or positive. That's all. So the communication engineer essentially concentrates on this DI. He designs and develops this DI. Of course, he does concentrate on PT also, but he carefully makes sure that DI is carefully designed such that he is able to detect a signal, recover a signal, and present it for the person who is interested in listening, using that. So what make a DI? What exactly do you mean by this DI? DI essentially is direct detection index. Based on the value of the detection index, we take the decision whether the signal has been detected or not. It essentially handles the noise effectively. Suppose there is an input SNR, there is an output SNR. Output SNR of the receiver system should definitely be better than the input SNR. That's the whole purpose of doing all these things. So to make up for the transmission loss, to improve take care of the noise, we must have a system such that output SNR is more than the input SNR. This ratio of output SNR to input SNR is called a processing gain. To improve the processing gain, what do? We limit the bandwidth of listening. For example, the signal comes in broad bandwidth, we limit ourselves to a small portion of that. So we limit ourselves in whatever the bandwidth that are necessary. And we do a post-integration for a T seconds or so, and we use phased arrays also wherever necessary. For example, in a band limiting filter, which has come up over here, the processing gain is minus 10 log B0 divided by BI. B0 is output bandwidth, BI is the input bandwidth. Minus sign has come up because B0 is smaller than BA, and if this becomes a fraction, to take out of the logarithm, minus has come. For post-detection integration, if we integrate for a time of T seconds, then correspond across n samples, then the processing gain is 10 log root of ns. And a phased array, if you try to form a beamformer across any elements, then the processing gain is 10 log ne. These are all facts and figures which are known to us. We'll just go to this phased array a little later, but these are all facts and figures very well known to communication engineers that are available at their fingertips. They make use of this extensively. They make use of band limiting. They make use of the post-detection integration and all that. Post-detection integration only says that we consistently watch and then only declare the integration. It's not that just like that when something crosses the threshold, we don't say it has been detected. We watch for that for a certain amount of time, T seconds, and then say that the signal has been detected. And strategy for detection obviously we know that strategy for detection is energy integration and replica correlation. These are the two well-known strategies for signal detection. That is, square and sum of the energy that is received, make sure that it is crossing out the threshold for detection. If replica is original signal replica is available, correlate with the replica and then see that the summed up values of the correlation are crossing the threshold. So these are two well-known techniques which are very well known to the communication engineers, which we had been using extensively. For your conviction, I just thought I would work out show you that if the BA happens to be 1000 kilohertz and B0 10 kilohertz, 10 kilohertz, then the gain from the filter is 20. And if you integrate over 8 samples, then it appears to be something like 23. So you can comfortably handle a worst case SNR of minus 30 dB. In fact, in some of our sonar systems and our underwater systems that we operate, the SNR is often worse than minus 30 dB. That means there is hardly any signal over there. We have to pull it out. For that, we make use of band limiting filters, post-detection integration, and phased arrays also extensively. If you can handle the signal, some of the signal in any elements, so you get a processing gain of 10 log ne. All these things you have learned from your signal processing fundamentals. SP has taught you extensively all these concepts, and you would have worked out sufficient number of examples and all that as you develop. We have been practicing it left and right. And that's where we have become mature communication engineers. Suppose there is no noise and you have to take care of TL. Then what's the way? What's the way out? Of course, even if there is a noise, you have to take care of TL. right approach is use a phased array. Band limiting and detection alone may not work out. We have to make use of a phased array. Let's see how the phased array works. Assuming that there is a far field object, far field source, which is transmitted signal, it sends a planar wave like this at a frequency of f. It comes at an angle theta and is received by an array of signals, array of sensors, which are spaced at d equal to d less than lambda by 2. D is interelement spacing, it is less than lambda by 2. So this quantity is d by d theta. So from this first signal, first sensor to second sensor, there is a delay because of this distance. That delay is equal to 1 by c d sine theta. C is the velocity by which the wave is propagating. And so we have got this wave that is coming over here, passes on these things. First it impinges this, then the next one, subsequently this one and this. And then as it moves on, we can delay all these things, but the first by 3 times, second by 2 times, next by 1 time, and add them up together. Because of that, it results in what's called a coherent addition. That their signals are added in coherence. When the signals get added and the noise gets cancelled out. This is the fundamental concept of beamforming. So we have normally we make use of linear beamformers only. Planar beamformers are also there when it stretches us in 2 dimensions. In some of the sonar systems, we make use of cylindrical array beamformers also. The processing gain, as I mentioned earlier, is 10 log NE. And so now think of a situation like the orbiter in satellite communication. The orbiter that is orbiting around moon is trying to send something to the geostationary satellite. Distance it could be something like 400,000 kilometers or so. So they make use of normally the transmission in some of the K band also, K or K band also, Q band, the K under band also, where the value of lambda is very small. So you can have large number of elements packed up together. The size will not be very large because the lambda by 2 is very, very small. You pack all of them together, and over a large number of elements, you get a fantastic gain of 10 log NE. This is how heavy attenuation and other things are taken care of by making use of beamforming. Some of the 5G systems also make use of this beamforming. And beamforming is an extensive gain because one plus the greatest advantage is signals gets added in phase, noise gets cancelled out. And the basic concept of this phased array beamforming is that you are actually listening only to a particular direction. The theta, you are in fact steering the beam in a particular direction to receive only from that direction. So it essentially what it does is to do what's called the spatial filtering. You have got data coming, the signal coming from all the directions. Some of them may be disturbances, some of them may be what you want. So we listen to that direction attentively so that we get the maximum amount of improvement of SNR. So it is essentially we are tapping on the directivity of the signal so that we get the best reception in that particular direction, knocking off all what we don't want from other directions. So we have been using this in radars, for example, extensively use signal the phased arrays. Sonar systems makes use of the phased arrays. Many of the 5G systems also nowadays are claimed to be using the phased arrays. So satellite communication systems also extensively make use of them. And so it has become very popular. The concept of the phased arrays beamforming is very, very, very popular now and is extensively being used. Let's come back once again to the model that we have for the receiver. In addition to all these signal processing aspects, we also have to worry about the basic analog circuit components. It is a requirement of an input amplifier, down conversion, and background noise removal through NEGC or TVG. Then spectrum normalization, because often we'll find that there is a 1 upon f characteristics. With the result, there's a predominance in the lower side. To remove that, we make use of the spectrum normalization, then filters and gain stages and all that, and then finally A to D conversion. And the digital signal is what is presented to the signal processor. Majority of the signal communication is now handled digitally, so naturally there should be a good digital conversion systems, and all sorts of high resolution digital A to D conversion techniques are used, like signal data converters and all that. You get high precision data, which is then passed on to the digital signal processor or other implementing systems like beamformers, then detectors, integrators, etc. All are then implemented carefully in signal on the DSP side, digital signal processor side. When it comes to transmission over longer distances to span over the cities or across the oceans, this requirement came up again because of the Second World War. Because there was a requirement to transmit world over to effectively wage the war. coordinate the activities in various directions. Nowadays, also people are making use of that extensively. This is achieved by converting data or signal into electromagnetic or light waves, encoding the information into digital or analog forms, transmitting it via cables or wireless frequencies. Again, let us remember Maxwell once again. Maxwell has given the basic equations, and if you just operate del cross over here and then readjust some of the basic, make use of some of the basic vector calculus identities, you'll be able to demonstrate that the physical temporal change in the electric field can result in spatial variation of the electric field. This shows how exactly waves can be transmitted. So this confirms that waves can be propagated by a temporal change that vary the physically in the time. And if you do that, there will be a corresponding variation in the space also. Signal will start propagating away. This is the basic concept behind the transmission over longer distances. Modulation over longer distances, obviously, we have analog modulation schemes. Amplitude, AM, FM, etc. have been there traditionally. Now, digital communication systems and modulation schemes have taken over. Amplitude shift keying, TDMA, FDMA with frequency shift keying, OFDM, spectrum, all those things are at our disposal. I'm not going to spend much time on this because all these things we know, we have been using it extensively and we are experts in understanding them and using them most effectively. Now, what did Marconi do? It is worth remembering at this point, what did Marconi do? He transmitted the Morse code corresponding to S over a distance of 3,400 kilometers from Cornwall in England to St. John's in Newfoundland in the USA, across Atlantic. He made use of high power spark gap equipment to generate a signal burst. Essentially, it was a burst because of the spark, and the receiving antennas were kept on mounted on kites also, so that he is able to get a proper reception. His success was in transmitting the signal S, the Morse code corresponding to signal S, some 3 dots or something like that he managed to transmit. Now, what I'm trying to tell you is that these have been some of the historic development, historic perspective also that tell us what have happened in communication so far. And we have the entire spectrum now available for communication. We have the lower bands, L band, S band, C band. Mostly these are all used in satellite communications for the to the ground stations. Then we have the X band, which is extensively used by the military only. Most of the military radars operate only the X band. U band and other K band and K band are normally used for satellite for the communication in the open space. Because of the very high frequency available over here, the throughput is very good. Lots of data can be transmitted, large amount of images and all those things can be captured and transmitted. And the reception, as I mentioned earlier, will be through phased arrays because they can capture, we can take care of the transmission loss and other things and then rebuild the images. We also make use of optical communication in some of the recent developments. Let's remember that at this point, it is worth remembering that the 5G spectrum operates in mid-band and high band. It is a millimeter wave also. These are the two areas where 5G spectrum operates over these days. And of course, in that process, they make use of, as I mentioned, this somewhere around the K band also. This is somewhere above this happens to be somewhere around the K band also. This is somewhere in the lower band. Whatever be that, they are making use of these things for communication in the 5G spectrum, where it is, of course, now the craze of the day. Everybody is now talking about 5G, where a lot of data, image, everything can be text, everything can be transmitted. So far, we have talked about traditional and known facts. These are whatever I mentioned are all things which already you know. I was only just trying to recapitulate, just to make a stage to talk to you more about what's new in communication technologies. Since you are all looking to get a perspective, a far-off insight as to what we should do in the communication, what we should know in communication technologies, let us look into that. See, machine learning is entering communication. See, now it is sarvatra machine learning. Everywhere it is machine learning. Wherever you look around, you have got machine learning. And machine learning obviously implies artificial intelligence. The ML algorithms are basically meant to implement artificial intelligence. The question is, what do you mean by intelligence? Let's listen to a famous piece from Kathopanishads. It says, Atmanam yadidam vidhi shariram yathamevatu buddhim cha saradhim vidhi mana pragrahamevacha. Defines buddhi, that is intelligence, very precisely. Buddhim cha saradhim vidhi. That the intelligence is like the chariot driver. You assume that you are seated in a chariot and the body itself is a chariot, and the intelligence is a chariot driver that is able to take you from point A to point B in very well in time, knowing very clearly about the obstacles possible, which is the best way available, and he is able to deliver you, take you to the destination. Again, earlier in the days of armed combat, the people used to mount onto this chariot and used to fight. There, the Sarathi decides whether the person who is standing behind him is going to win the war. Because depending upon the opposition that is available, depending upon the situation, he makes a situational assessment and accordingly drive the chariot in such a way that the person who is behind him actually is able to hit the target and then win the war. Basically, it means that the Sarathi, as the chariot driver, is an intelligent person. He learns from his experience and uses his experience to take the further decisions. So, Buddhim cha Sarathim Vidhi means being able to learn is the essence of intelligence. Any system that is capable of learning from the experiences already acquired is considered to be an intelligent agency. It's not repeatedly doing what something is asked to be done. We can learn out of that and use it carefully in the subsequent decision making in the subsequent applications. That really implies an intelligent activity. So, Buddhim cha Saradhim Vidhi. Let us remember that. So, the communication system now gets redefined. There's a machine learner on the transmitter side. There's a machine learner on the receiver side. That gets interposed so that system becomes more intelligent. Communication system becomes more intelligent. So, what are the ML models available? The standard ML models which are used are autoencoder, then the convolutional neural network, then the generative adversarial neural networks, and variational autoencoder. These are definitely some of the new concepts some of the concepts which are extensively being used. Autoencoder, as you can see, captures the data and reduces it to a very small dimension, and then is able to regenerate it faithfully to what was received. So, in this process, without any kind of information loss, it is able to regenerate this. So, this is very effectively used in some of the source coding, so that the source data can be drastically reduced and transmitted, and it can be recovered without much of any information. CNN, as you can see, convolutional network is actually a layered network. It is spread across different layers, and it is also a fully connected network. Because of the various kind of convolution and other kinds of activities that are taking place at various layers, is highly adaptive to the various environments. You train with certain amount of data, and then as you try to input data which are very similar to whatever that is used for training, even if there are variations, the recovery is fantastic. So that means these sort of systems have demonstrated an excellent mechanism to be very adaptive, can handle a large variations, sufficient variations in input data, and then give you the correct answers. So convolutional neural networks are in fact evolved from the basic neural network technology only, but they added multiple layers and introduced concepts like max pooling and all those things, and then is able to now handle the variations which are likely to be existing in the incoming data very effectively. The generative adversarial network is a mechanism by which the incoming data, even if it is sufficiently small, can be compared against what is generated from a random noise. Random noise, as you know, is broad spectrum. It consists of all spectral components, contains good amount of information, complete information. So you design a network, design a network and adjust the weight in such a way that the image that is generated and the image that is received and the image that is generated are matching, and any match is actually conveyed as a positive response. Any mismatch is conveyed as a negative response, and accordingly you adjust its weights over here, both the input as well as at these points, and you are able to generate an image which has got characteristics which is similar to what is used for the training. You don't have to have all the large amount of data for this, because once you train it to a certain amount of level, because random noise is being used for driving the basic data, it is able to regenerate without much difficulty most of the information corresponding to the incoming data that are used for training very effectively. So GAN has been extensively used for generating large amount of data for training and other purposes. It's a very effective tool for handling generating large amount of data. The variational autoencoder effectively computes the mean and the variance of the incoming data. As you give the incoming data, keeps on computing the mean and variance continuously. And then when it comes to regeneration, it essentially samples a Gaussian space, and then this is essentially the sampling process, and then decodes and generates an XCAP. That means many samples are generated and you choose the one that is closest to the input during the recovery. So this error x minus x cap the whole square is minimized. So you choose that one, which is basically the one that is closest to what you are giving as input over here during the recovery. So you train with a large amount of data. Essentially, you are computing only the mean and the variance. And of course, there's a Gaussianity implied in that. We are assuming that the distribution is Gaussian. So we are sampling a Gaussian space and regenerating the data. These are some of the well-known ML models this ML community has developed. And as you know, Python, R, everybody has got the supporting tools available for this. Only question of you being able to use these things effectively. For example, how many layers are required to be given over here? What's the kind of the reduction that is required in the data? And over here, how many layers are required over here? When it comes to max pooling and all that, how to really max pooling effectively reduces replaces every 2 by 2 area in the network by one single element. And of course, all other activities over here are designed by the person who is using it. And as you know, the training of the system is obviously by backpropagation. You try to find out the error between what is given over here and actual data. The error is propagated backwards, and backpropagation is used to train the network so that the networks operate to handle cases which are quite different from what is given as the input also. Input, of course, it handles very well because it has been trained for that. Even if you give an input which is different from the what is used for training, you will be able to get a recovery without tremendous amount of adaptability. So these are some of the models which are now extensively being used. The predictive and the adaptive capabilities of ML helps a lot to improve the data compression, error correction, and overall transmission efficiency. That's how communications engineers have been attracted towards that. It definitely makes the system more robust and efficient. So let's have a look at the complete communication system. It's machine learning included. We have definitely the source, then the source coding, channel coding, modulation where you do the up conversion, transmitter and transmit beamforming is there for that because of the beamforming properly. Then we have the receiver beamforming, down conversion, signal detection, channel decoding and source decoding to recover the signal. Any of all these modules are now augmented by proper components of machine learning. That's where, of course, wherever possible, they are trying to incorporate machine learning in this so that the overall efficiency, the capability, and the adaptability of the communication system is enhanced very much. It becomes highly versatile and most effective. Coding and decoding techniques, very vital in digital communications, ensuring efficient and reliable data transmission. Traditionally, we have the source coding, for example, data compression of different types, and the channel coding essentially to introduce additional data to take care of error correction. We had been using it extensively. There are so many parity checks and all those things had been there in the channel coding. Source coding also, there were a lot of good amount of algorithms available. But when it comes to ML techniques, we essentially make use of neural network autoencoders. Remember, we had seen that the autoencoders earlier can drastically pick the data from a large dimension to a small dimension and recover it without any loss of information. That's the capability of an autoencoder. So if you make use of an autoencoder, slightly different from the traditional techniques, we will be able to have a excellent implementation of source coding. Autoencoding learns efficient representation of data and ensures high compression rates with minimal loss of information. Now, when it comes to channel coding, all those things like LDPC, etc., are effectively implemented by making use of neural networks. ML models, for example, variational autoencoders, convolutional neural networks, and generative adversarial neural network. All of them jointly learn the representation and the error detection codes. So they are able to recover the data very effectively. All these things result in offering improved performance over the traditional algorithms, especially in highly noisy environments. Now, please understand that I am not going to here give you a kind of a tutorial review of all these techniques and the effectiveness, but to tell you, these are some of the techniques that people are extensively using nowadays. Tools are available extensively, so we are practicing on that, and they are able to achieve excellent results when it comes to the various aspects of communication. Here, as I mentioned, the source coding and the channel coding. When it comes to modulation, modulation is basically a trick of altering a carrier's signal properties, amplitude, phase, or the frequency or phase to encode the information. We have traditionally the amplitude modulation, frequency modulation, and PSK, phase shift key. Adaptive modulation schemes mostly employ ML techniques. Particularly, deep learning networks are extensively used. ML models, the advantage of ML models is that It is able to adjust the modulation parameters. Modulation parameters requires how much of variations are required for the input frequency that are used, or what's the kind of ratio in which the energy has to be combined. This is adjusted by sensing the conditions of the channel. As you transmit in a channel which is having large amount of variations. For example, now it's very raining very heavily in Kerala, as you can see. Some of the communications in C-band and extended C-band heavily get activated during that process. So naturally, they try to see that what exactly the frequency is learned during on the run, and then try to using ML models and adjust the parameters in such a way that the performance is optimized in real time. Neural networks learn complex modulation patterns to maximize the data throughput and minimize error rates. When it comes to detection, demodulating the received signal to recover the transmission information is basically the concept of detection. We all of us have been using it extensively. The traditional methods rely on predefined algorithms, estimate the transmitted data, often assuming specified channel characteristics. For example, we assume that there's a certain amount of background noise. Usually, it is assumed to be Gaussian noise. Sigma and sigma, etc. are normally assumed, and when we try to define our detection system. We very well know about the Neumann-Petersen criterion for energy detection and replica correlation. It looks like this. There is a noise-only condition. There is a noise plus signal condition. And we've tried to find out a threshold here like this. And then, depending upon this threshold, this crossing point, the threshold for detection, depending upon this crossing point, threshold for detection is calculated and decided, and accordingly we declare detection. Remember, this has been this has become a kind of a game which an operator performs. Sitting in front of the receiver, he tries to play around with different values of threshold and try to find out when he's getting the detection. He doesn't really try to understand what is the noise condition prevailing in the background and what is the kind of signal plus noise ratio and all that. He doesn't know about that. For example, when we had been operating the sonar systems, we used to sit in front of the receiver. Sonar systems also transmit the data. Only thing is, it is wireless, transmits sound only. That's the only basic difference. It doesn't transmit electromagnetic waves. It transmits sound. So when we receive the data on a sonar system, we keep on playing around with the threshold for getting a good detection. But remember, threshold alone is not sufficient. You should know what is the kind of noise characteristics, what's the noise level, whether it is Gaussian, is there a deviation from the Gaussianity. All these things have to be understood. This crossover point has to be carefully understood so that the threshold can be worked out for replica correlation and energy detection. Which we don't do. We try to only play around with the threshold and see when we are getting the detection. An ML approach, on the other hand, learns from the origin from the data, accurately detect the signal under varying and complex channel conditions. As the channel conditions vary, you know what exactly is the kind of signal corruption, what is the level of the signal corruption, is it Gaussian or is it any variation from the Gaussian? All these things are understood and accordingly design very efficient approaches to detect the signal. Definitely, it helps to improve the robustness and against noise and interferences. Deep neural networks and transfer learning. Transfer learning is a process whereby you learn, transfer the data that is already acquired from one level to another level. For example, if you operate the system for some time, you receive a certain amount of information, use it, stock it carefully, and use it effectively for the next time when you want to have the when you want to operate the equipment. So, deep learning, neural networks, transfer learning, etc., have been employed very effectively to detect this detection most effectively. Because I can very well appreciate this because in the sonar systems that we operate, we have been playing around we have been playing around with the threshold only, often finding it very difficult to get a meaningful detection. Whereas if the system itself can learn and come up with a proper mechanism to define the detection threshold for the background, then it becomes a very good support for the operator. As you know, all these things are being designed only to support the operator most effectively to improve his performance and improve his performance during the operations. The transmit receive beamforming. Beamformer, as I said, is essentially doing a special filtering. We have understood that some time back. It directs the transmission and the reception signal. For example, transmitter signals are collimated in a certain direction. You listen to selectively to a certain direction and get it only from that. Essentially improves the signal strength and reduces the interference. That's the purpose of beamforming. So you can see, for example, suppose there is a DNA array, you can form the beam in different directions. We say that I formed a beam in this particular direction. I formed the beam in this particular direction. When I form a beam in this direction, only what is coming in this direction is received. Other interferences and other things which are coming from this direction are all thrown. So if you want to continuously listen to that, you can track in that particular direction, continuously receiving and rejecting the disturbances from other directions. So this is a traditional way of beam forming. It's the basic theory of beam forming. You form the beams. Beam patterns are adjusted in such a way that you selectively listen to a known direction, a direction of interest. So what happens when you use traditional techniques in transmit beamforming? We define predefined algorithms to adjust the phase and the amplitude and give them to the different signals. The source, the transmission takes place, and everything gets summed up in the medium, and it goes as a sort of a collimated transmission in one particular direction. You can very precisely pinpoint which direction you have maximum energy. In contrast, ML techniques, particularly deep learning models, optimize this process by learning from the environment data. Decides how exactly the delays and the various weights which are used for this summing. It essentially uses a delayed weighted sum. How the weights are required to be generated so that the transmission becomes effective even when there are varying conditions. For example, in underwater, for example, if you look at it, there can be a lot of variations because of the disturbances below the sea, in the sea water. Similarly, same thing happens in atmosphere also because of the rain, shine, and other kind of all sorts of problems. The transmission gets disturbed. So, sensing the requirements, deep learning network can do this and can adjust the parameters such a way that the beam forming becomes most effective. Beams are formed in such a way that disturbance is minimum and you get the maximum signal reception. Reinforcement learning also takes place where the dynamically adjusts the beamforming patterns in real time based on the feedback from the communication environment. Depending upon how the data has been received, learns from the communication environment and adjusts the parameters. Parameters, I said, similarly looks like weights in the summing elements, and also the delays and all those which are used are all adjusted dynamically so that it becomes reinforced learning. And in that process, it is able to receive very effectively, suppressing all the disturbances on the unwanted directions. When it comes to receiver beamforming, we had the traditional techniques of MVDR, that is minimum variance distortionless receiver, maximum ratio combining, and delayed summing and all that. All depending upon statistical assumptions that we assume certain noise variance for the noise that is present in the system, and the weights are calculated on the basis of that. But then what happens is once these noise variance change, or the noise characteristics change, these things may not work out very effectively. We had the experience of that because MBDR had been, for example, a high resolution beamformer. It works out very well when the conditions are all favorable. But if there is a drastic variation, obviously there are reasons for failures also. It doesn't work well. ML approaches such as convolutional neural network learn the optimal beamforming weights directly from data. The weights are directly learned. Here, the weights are obtained out of a optimization technique. You optimize certain functions and then learn the weights for a particular assumption. Here, on the other hand, based on the background situation, you are learning the beamforming weights directly from the data, allowing more accurate and robust. As you know, this is very essential to take care of the various kind of disturbances that you are likely to face during the transmission and reception. Channel degradation and recovery. Signal transmitted through the communication channel faces various impairment issues like intersymbol disturbances, Doppler shift, and fading effects, etc. How to mitigate the effects of this channel-induced impairments? The use of adaptive filter. This had been well recommended for communication engineers. Use an adaptive filter or equalization. Nullify the effect of wireless channel and recover the original transmitted data. Mostly we use an FIR filter whose coefficients are computed based on the minimizing the error in the transmitting known signals. What's called adaptive channel equalization. We had been using it. So channel estimation, essentially in ML techniques on the other hand, channel estimation generates channel properties and provides necessary feedback to transmitters and receivers. Traditional methods such as minimum variance, minimum squared error, or rely on statistical models and require significant computational resources and are made on certain assumption of the background. Machine learning approaches, on the other hand, dynamically adjust and is able to generate the data corresponding to the situation in hand. And essentially the parameters corresponding to the situation in hand. And therefore, the system becomes more effective during operation. So the communication system becomes more effective during the operation. The traditional FIR filter, adaptive equalization, is what is picturized over here. You have the equalizer whose weights are adjusted based on the signal that is detected and the signal that is received over here, and you try to adjust this error, which we had been using in text to series. We know about this very well. Now, when it comes to the neural network model, for example, they make use of an auto-regressive model with exogenous noise. For example, the current value is a function of past few samples, certain samples of input in sequence, noise components, and of course a parameter theta. This essentially the XK regresses or depends upon all these things. You definitely have, normally we make use of a linear regression with a non-linearity over here, or any other function can be introduced. Then this comes to then you can make use of a neural network for this. When you have the can form a weighted sum with a neural network of all these inputs, that is the noise components, the input components, and the delayed values, whatever that is available, whatever that data that are available at the output are delayed and corresponding different values, and they are all summed up, and the weights are minimized over here. You know what is the current sample because it's actually assumed as a time series. So the current value is available to you. Try to predict the current value, find out the error, try to propagate the error backwards using standard back propagation or any other method. Some of us have been using even techniques like Kalman estimation and all that, even random forest and all those things have been used to compute these weights, such that the weights which are as parameter over here can be effectively computed. So after the weights are, so in that process, you essentially try to bring down the error during the training, and the error comes to a certain low value. Then by cutting off the training process, you can continuously generate the data. You give the input and the output gets properly generated. So this is the basic idea of nonlinear techniques. Of course, what happens is after a little while, when this background situation changes, it starts diverging at this point. This has got to be understood, and you have to once again do the training so that again the error is kept within the minimum. Semantic communication. Now, this is one of the major development that has happened because of the machine learning techniques. Focus on transmitting only the semantic information, not the entire bitwise data. For example, you can transmit the image, text, or audio, the content of that, descriptions of that, to the receiver side and regenerate if necessary. It reduces overloads of transmission orders, transmission wireless channels, reduces overloads of wireless channels. Also, information transmission speed and efficiency can be considerably improved. Lot of channels can be multiplexed together. You can combine channels together, and throughput also can be improved very. So essentially, you extract the information from the data, transmit only that information, then the receiving end, if necessary, rebuild the whole thing or assume the information as such. Very often, you are only interested in the information, not the complete data. So deep learning models, including transformers, convolutional neural networks, and recurrent neural networks, are used extensively for this. They analyze and predict the semantic relevance of the data. The natural language processing and NLP and the computer vision methods also play a significant role in this. So this has become very popular nowadays. For example, some of you maybe would have come across this kind of a picture when you look at the cricket score, cricket matches. Now the football matches are going on. When it comes to cricket matches, where there is, of course, the changes take place incrementally. As you look at your mobile, you'll see that because you are not really interested often in the complete video that is going over here, how he is actually rubbing his ball and then try to increase the shining and all that. You are interested in things like what is the score right now, what is the asking rate, what is the score rate, and when exactly a wicket fell off, and whether there was a maiden over, somebody made a maiden over, bowled a maiden over here, and the batsman is not very active, batter is not very active, bowlers are scoring over here, because continuously nobody is scoring any runs. And this kind of information gathered, the condensed information comes to you, which is all what you normally require. Especially when you travel by somewhere, you can just keep on your mobile and find out what exactly is happening, rather than making all these conclusions yourself by exhaustively watching the video updates. Often that becomes very exhaustive, and you have to remain glued to the TV or the mobile to essentially get this kind of information that when you receive it from the video data. Here, the semantics, the essential information is all what is collected and presented to you. Of course, now an AI system, if necessary, can regenerate all this data also from this input. They can very well regenerate the data and present the video, so synthesize the video and give it to you. But that's not really interesting. Like when it comes to the matching the cricket match, this much of information is more or less required for sufficient for us to appreciate the progress of the match. I was wondering what exactly the optical communication community has to do with this non-linear, the ML techniques. Because if you look at the optical communication, there is an electrical signal which is converted to optical signal using an electro-optical converter, goes to the optical fiber, and it's a wired connection incidentally. It is received on the other side, and the signal is electrical signal is recovered. So these things are fairly straightforward, and we think that what's the great significance of ML over here. Interestingly enough, in the physical layer, the non-linearity which is likely to take place is taken care of. Non-linearity mitigation is one of the basic requirements of ML over here. Optical fibers suffer from non-linear effects that degrade high-speed signals over long distances. So deep neural networks are Volterra filters. Volterra filters are actually quadratic filters, bicod and quadratic filters, which can accurately predict and compensate for these non-linear impairments. And it performs much faster and with better accuracy than traditional methods. So the the degradation that is likely to take place during because of the transmission over longer distances, even if it's a wired network, physically a wired network, will be taken care of by these machine learning techniques. When it comes to the modulation and demodulation, unsupervised ML algorithms like k-means, etc., are used extensively to identify and compensate for signal distortions. Suppose the received signal comes up with a certain amount of distortion, as the pattern changes or the data samples vary. It doesn't mean that the data samples, the value of the data samples vary. You can have a kind of a k-means clustering and see that the outliers are all rejected properly, and it therefore helps in IQ imbalances, taking care of inverse and quantized component imbalances, laser phase noise, etc. All these things are taken care of by ML algorithms. When it comes to performance monitoring, the ANNs definitely play a significant role. You can find out, as you said, monitoring at the output, you can find out whether the performance is degrading or not. From the signal to optical noise ratio can be computed online without really having to assume all those things. Network layer and when it comes to the network layer and orchestration, software-defined optical networks, ML manages routing, spectrum allocation, and hardware phases. The routing, for example, as you know, the routing is a major issue. Of course, not necessarily in optical communication, of course, where it is mostly wired, but still you have to see how to avoid the data congestions. Data has to be properly routed in different directions so that it is received in time, well in real time, without any kind of disturbances, without any kind of a mitigation. So the traffic prediction of the traffic is extremely important. For example, I am aware of the methods where in mobile ad hoc networks, we try to find out the path from the source to the receiver. This, of course, is very difficult because being an ad hoc network, you don't know where exactly the individual repeaters are. And what is their status, whether they are ready to transmit or not, what is their health, is not very clearly known. So the traditional way of doing that is to do what is called a packet flooding. On end, you send a flood of packets and find out where exactly you are getting the maximum return. Depending upon that, you find out that, conclude that that's the best transmission line and transmit only along that to get what is called a maximum packet delivery ratio. But currently now people have been using other techniques like belief propagation and all that, which is established statistical techniques, and try to see how exactly the best people, you assume that the uncertainty involved in each of these sensors en route are assumed as some kind of a random number generator, and accordingly you are trying to find out the probability of the signal going from one point to another point along the transmission line, and then in that process you try to find out which is the best continuous path that is available. This we used very effectively in mobile ad hoc network, where of course it is wireless. So when it comes to using that in the case of even wired networks like optical communication networks, to avoid the congestion and all that, to make sure that the data is delivered and the packet delivery ratio are also kept high, you can make use of recurrent neural network techniques and all that. And of course, it also has to do what's called a failure prediction. As I was mentioned, the failure is something that takes place progressively. It doesn't happen all of a sudden, especially whether repeaters en route. depending upon the condition of the performance of the output, you can predict and find out when exactly a particular node is going to fail, and accordingly redirect. So link prediction. Otherwise, you will know that only after the link has failed, only you will know that it has already happened. There is no signal going to that. You can predict that properly and find out whether to reroute your data to some other link. In MANET, it works out very effectively. The same thing they had been using in fiber optical networks also. And when it comes to routing and spectrum allocation also, reinforced learning and other things are used extensively. In summary, ML is steadily entering into all functional stages of communication systems. Ready communications engineers have achieved a lot in communication. Okay, I sincerely appreciate that whatever that we see around these days for getting our data, text, video, etc., all have happened because of the excellent communication foundation that the communication engineers have laid. Now, it is up to the communication engineers to equip themselves with skill and techniques, ML skills and techniques as we move. As we move on, let us try to see that few techniques that are available are brought into our specialization, and we learn them properly, we appreciate them properly. As I said, plenty of tools are available, so it's up to us to pick the proper tools. Trim the parameters carefully. Input parameters have to be carefully given to them so that the system operates more effectively, and there's tremendous amount of adaptability. For example, many of you must be aware of a concept called digital twinning, which I think has become a pet topic for the computer scientists nowadays. When there's an operating system, you try to generate what is called a twin corresponding to that. The twin, TWIN. The twin essentially learns during the operation process what are all the parameters that are set, how the system is responding, what are the results that are generated. So it learns both from the mistakes as well as from the correct actions. And then over a period of time, it is able to advise an operator as to what should be and how exactly you should operate the system. For example, think of a situation like this: military action control. Remember, here people are using this not for fun, because it is highly a very stressed condition under which they are operating. They have to communicate and they have to equipment or operate their equipments like this, their firing systems and all that. These communication systems, of course, there is a fear of loss of life also during that time. So when you have this sort of a situation, the digital twinning and other kind of operations, other kind of support, which are contributed largely because of machine learning techniques, will help you a lot in understanding, in operating the system more effectively. Operator fatigue and failure are often taken care of because of these actions. Otherwise, there has to be a trained, seasoned commanding officer sitting behind you who should advise you. But even the commanding officer can also become weak over a period of time. The digital twinning absorbs the data, corrected decisions taken, learns along with it, keep them along with that. Even the failures are learned and understood, and then advise you on to what exactly should be the how you should give the parameters, how should you set the threshold, how should you set the various parameters, integration parameters, etc. during the operation of the communication system. I cannot complete this presentation without a mention of my mentor, Professor Arogyaswamy Paul Raj. He's a professor emeritus at the University of Stanford, California, USA. In fact, Paul Raj is famous for his patent in MIMO SG. MIMO is multiple input, multiple output SG, where from the transmitter side and you put multiple transmitters and you put multiple receivers and combine the data to effectively increase the throughput. Lot of data can essentially increase the speed by combining all these things. So in Paul Raj's onwards, MIMO uses multiple antennas, a transmitter and receiver to multiply link capacity. And of course, he has been saying that people have been extensively using that. He sent me this presentation sometime back because in some other context, and I am taking the liberty of using that once again while presenting before you. Now, Paul Raj is remembered by us not for this patent in MIMO only, because he is the person who developed the first indigenous sonar for Indian Navy, and he was Commander Paul Raj working for Indian Navy. He was a project director for one of the projects in the Naval Physical and Oceanographic Laboratory where I had been working. I joined this institution way back in 1978 after post-graduation from IIT Kanpur to work under Dr. Paul Raj. He taught me how to design sonar systems, how to operate the different kind of input amplifiers, different kind of signal conditioning and all that, and various aspects pertaining to its development, development of the system. to attain the specific detection levels and all that. And we designed and developed and gave the first indigenous sonar, APSO, Advanced Panoramic Sonar Hull mounted, for some Leander class of ships also for Indian Navy, some class of ships for Indian Navy. And believe it or not, thereafter, Indian Navy never imported a sonar. It has become totally indigenous. Technology has been taken over by Bharat Electronics. It's a public sector undertaking. Variants have been developed of that because what we developed is a 1978 technology, must be very old. When MSI was popular, medium scale integration was popular. Now with large scale integration and all these kinds of new technology available, my colleagues are in the subsequent days define better sonar systems, but all indigenous. The technology for designing sonar systems is fully 100% available in industry for ships, submarines, and all other kinds of systems that the Navy uses. I thank personally Professor Polraj for having given us this opportunity to learn the sonar systems and then get into the area of wireless transmission. Of course, for sonar underwater, it is wireless transmission. What we use is sound. Of course, in air, they make use of electromagnetic. And when it comes to underwater communication, also, as I said, we make use of sound only because sound is all what can be transmitted. Electromagnetic waves get attenuated heavily in the saline water. So we make use of all the similar technique like MIMO, of course, MIMO and other things, and also orthogonal frequency division, multiplexing, etc., are extensively made use of. We do have problems because of the Doppler effects. The orthogonality across the different carriers will not be very proper all the time. So there are ways of correcting all that. People have been working extensively on that. And so we are able to effectively transmit text, video, and audio underwater. Of course, distances are relatively small as against the what is happening in air, in either open space, but still effective communication has been made possible. People have been trying to use lasers also recently. I'm not quite aware of that developments in that direction. So what I'm trying to say is that maybe over a period of time, MIMO and other things also will play a significant role. I would like to give a salute to my Guru Professor Polraj as part of this presentation. Now, if you look at the source separation in 5G, there's a basic issue here. Just understand that. You are summing up the sources from different directions. What happens in that process, lower order statistics become very prominent. You are not able to identify, separate them out. There's a thorough mix-up. Higher order statistics are practically similar. So we make use of a demixing network where the higher order statistics like the fourth order moments and higher moments are maximized. You maximize them and try to find out an adjusting factor so that the weights over here in this combining network, there's a combining network which you try to put over here. The weights in that those combining network are adjusted depending upon the results that you are getting by maximizing the higher order statistics. There's the idea normally which is given in the textbooks of Simon Akins and others. They talk about these sort of techniques. I'm not quite sure as to what exactly my colleague, my Guru Professor Polraj has put in his MIMO system, but the concept seems to be very similar that the overall statistics which is present in the mixed signal have to be definitely replaced by higher, have to be improved by improving the higher order statistics in the output signal so that there is good amount of separation. Because here the basic problem is that of delayed mixing. That is, there is a direct reception. There is also a reception from other direction. There is a delay. That delay is random. And because of this, often the signal gets highly deteriorated. It's the basic idea of the problem of MIMO systems. And these are some of the techniques which people have been making use of. Maybe there are a lot of improvements because I find plenty of papers coming up in this direction every day. And ML techniques are also being used in the process instead of really going for robust maximization of the higher order statistics and all that. Recently I found that there are some papers that talk about ML techniques also where they use for demixing. I'm not in a position to lay my hands on that fully because I not understood all those papers also fully. But I think over a period of time, ML techniques also will play a significant role in doing this demixing. So, as I mentioned, we have already seen this ML in military. Military requires a lot of ML support so that the fatigue of the operating staff can be taken care of, and you can wage an effective warfare with loss of life, human life. So to sum up, signal processing improves. Signal processing, we have learned enough of signal processing, essentially improve the signal quality, improve the SNR. So the only idea of signal processing. Extract the information and present it. But when it comes to what exactly happens when it comes to ML, ML empowers electronic communication systems engineers to better be equipped to design communication systems, augment your expertise, get more powerful and effective communication, And when it comes to extraction of information, ML plays a very significant role. We had seen the power of semantic communications, how the effective information contained in the transmission can be properly captured. The textual, meaningful, the textual information, the actual idea behind the transmission data can be understood. If necessary, you can regenerate it, or you can simply assimilate it as it is. So with this kind of power that is available, it's essentially that communication engineers should now enter boldly to the world of machine learning techniques, use them effectively wherever possible to improve the performance of the systems that they are operating and the systems that are generating. This direction, as I mentioned earlier, digital twinning now seems to be a very promising area that you can try to twin. Digital twinning essentially runs on some kind of a blade server, one or two blade servers, takes all the data from the output of a receiver system, and then understands what are the operating actions and all that. It has got a learning system, because during the entire operation of the receiver, a lot of data comes up. And all this from the data that is available, because as you know, all the ML techniques are data driven. You have to get plenty of data to train the system. It learns from the training data, and then over a period of time starts advising the operator how exactly you should prioritize his different parameters and how you should fix different parameters so that the system becomes more effective. So I would like to conclude at this point, thanking you all for the patient listening. Thank you very much.
I think you may open for the questions. Maybe people can unmute and you can ask questions, please.
Now, please understand that this communication had been heavily dominated by classical signal processing, statistical methods, and all that. On that, now you are getting into an area of machine learning techniques. I'm not saying that it's a diluted way. Definitely, it is making you stronger. You have to understand it. You have to have a base of classical techniques and to see how exactly the new techniques are going to augment your capabilities. In various areas, we have seen that coming across detection, modulation, and all these things. How exactly the ML techniques are going to improve your capabilities. Extensive material is now available. A lot of research papers are being published. I invite all of you to look at those things seriously. A large number of tools are also available, Python and R and all that. Use them extensively so that you are able to augment the capabilities of the existing systems more effectively than what it was earlier.
Thank you so much, Dr. A. Unnikrishnan, sir, for that wonderful session. Before we conclude, we would like to open the floor for a brief question and answer session. Dear participants, this is your opportunity to ask questions, seek clarifications, or share your thoughts with our resource person. Please use the chat box to type in your questions, or you may raise your hand by using the raise hand option on the screen, and we will unmute you.
Good afternoon, sir. Myself, Dr. Prajun from EC Department, Jyoti Engineering College. Thank you for the informative session. As communication technologies are evolving rapidly with AI and 6G, satellite communication and intelligent network, which research areas in communication engineering do you think offer the greatest opportunity for young researchers today?
Yes. So in fact, there had been a recent increase in even the minds of youngsters to go for electronic communication engineering. Basically, because instead of the traditional techniques, you can apply new techniques like machine learning and all that and produce wonderful results. This has become, therefore, it has become very attractive. And see, as I told you, over a period of time, the communication technology has been largely dominated by classical methods. And we have to have a thorough knowledge that we have been extensively using statistical methods and all that. Now, in addition to that, you are being equipped with other methods like ML techniques and all that, by which the system operates more effectively, more efficiently. And definitely that should give a way for the communication to attract more minds into communication systems. The design, development, and operation of communication systems. Hope I have
Sir,
answered
any
your
more?
question. Yeah. Yeah. Yeah, please.
Okay, thank you. On behalf of the Department of Electronics and Communication Engineering of Jyoti Engineering College and on behalf of participants, I extend heartfelt gratitude to Dr. A. Nikrishnan sir for this truly enriching session. Your session has been a remarkable journey through the evolution of electronic communications, shaped by decades of high-stakes research at NPIL DRDO. Your perspective gave us a rare vantage point, tracing the arc from early systems to today's intelligent network world. The clarity with which you mapped this evolution and the thoughtful direction you pointed us toward was deeply instructive. We are honored to have had you with us. We wish Dr. Unnikrishna sir the very best in all future endeavors, and we hope to have the privilege of your presence and guidance again.
Thank you. Thank you very much. Thank you very much for your patient listening. I do not know how much I have been able to impress upon you about my thoughts. But thank you very much for your patient listening.
Thank you, sir. Thank you very much, sir. Namaste. Thank you.
We will now take a short break. The next session will begin at 1 p.m. Please be ready and logged. Thank you, sir.